Thank you very much. My talk is going to be about creation of hypoxic mixture in the anesthesia circuit, how to avoid it. So I'm really going to be talking about hypoxic guards. So how do we ensure that the FiO2 is higher than 21%? We have to administer enough oxygen to our patients. We should be doing continuous measurement of FiO2. That should be standard of care. But then our anesthesia machine manufacturers introduced hypoxic guard systems, and that happened in the 1970s. There is very little literature about these hypoxic guard systems, but anyhow, the anesthesia machine manufacturers were very responsible, and they developed systems that helped us to avoid the administration of hypoxic gas mixtures. Very good. The anesthesia machine standards appeared around the year 2000, so the practice of introducing the hypoxic guards came before the standards were made. Kind of bizarre. So what are these anesthesia machine standards? The first standard says that the anesthesia workstation shall protect against an oxygen concentration below 21% in the fresh gas or in the inspiratory gas. You can choose. And the second anesthesia machine standard says that there should be equipment to prevent the unintentional selection of a mixture of oxygen and nitrous oxide having an oxygen concentration below that of ambient air. So it's remarkable that these anesthesia machine standards only talk about oxygen and nitrous oxide mixtures, and they focus on the delivered concentration of oxygen, not the inspired concentration. So if we look at the definitions again, we can see here that the FD is the delivered concentration, while the FI is the inspired concentration. Very big difference there because of the effect of rebreathing. And with lower fresh gas flow, we have rebreathing of exhaled gases. And that's not just true for the potent inhaled anesthetics in the exhaled gases, but it's also true for the carrier gases, oxygen, nitrous oxide, and nitrogen, air. So the original hypoxic guard systems that were developed by the companies were really mechanical pneumatical systems. So the first one that I'm going to describe is the Datex Omida Link 25 system. Was patented in 1979. I don't know exactly when it became clinically available in their anesthesia machine. There is, as I said before, very little literature on all this stuff. It's used in the Datex Omida XL series, and it was very simple. It ensured a delivered oxygen concentration of more than 25%. It said nothing about inspired concentration. And it really was a link. There was a mechanical link between the inspiratory rotometer and the nitrous oxide rotometer and the oxygen flow meter. So there was a physical link. That's why they called it the Link 25. The technical details on how many TTs these cam wheels have is not really relevant for this talk. It's very nicely described in one book chapter on this, but for us it's irrelevant. The other hypoxic guard system was developed by Draeger, and it was originally called the ORMC, and that's still used in some of the older North American Draeger anesthesia machines. A second system that was developed by Draeger is the sensitive oxygen ratio controller, the S-ORC, and that is used by the Draeger Fabia series. So I'm talking about the mechanical S-ORC system. Now the S-ORC system is relevant because it was more stringent than just requiring a delivered concentration of oxygen of more than 25%. It went further than that. It said we should have not just an FdO2 of 25%, over 25%, but also there should be a minimal fresh gas flow of oxygen of 250 mL per minute. To the best of my knowledge, these thresholds have been chosen arbitrarily. There is no reasoning to it. Although you could think that there is a reasoning. The first criterion looks very reasonable. The second one looks reasonable also because it's just above the oxygen requirement of an anesthetized patient. So you might think that it makes sense, but I'm not sure that this has ever been studied by the companies when they implemented this. So the result is that the hypoxic guard limits of the S-ORC system are described in this curve, and the curve is the result of these simple calculations. If you have a total fresh gas flow of 1 or more liters per minute, and you want a FD of 25% or higher, then these have to be the fresh gas flows. So in other words, if you have a 4-liter total fresh gas flow, the S-ORC made sure that you had a 1 liter per minute oxygen flow. Below 1 liter per minute total fresh gas flow, it became trickier because then the other rule came into place, at least give 250 mLs of oxygen per minute. So if your total fresh gas flow is 250 mLs per minute, and you have to give 250 mLs of oxygen, then your delivered concentration is 100%. So this graph is the result of their two criteria, at least 25% FDU2 and at least 250 mLs of oxygen per minute at any fresh gas flow rate. So the problem is when we start the low fresh gas flow, because again, we not just have rebreathing of the potent inhaled anesthetic, but we also have rebreathing of the carrier gases. And the exhaled gases have a lower oxygen content than inhaled gases. So if you mix the exhaled gases and you rebreathe them in, you lower the delivered concentration of oxygen towards the lower inspired concentration. It's a dilutional effect, the result of rebreathing. And the more rebreathing you have, the larger the difference will be between inspired and delivered oxygen concentration. So this is a description of the Draeger S-ORC system, where they use pneumatic interface with a mechanical bar that at certain points when there is no oxygen or little oxygen flow will reduce the amount of nitrous oxide flow. So it's a mechanical device. So these original hypoxic guard systems were developed to maintain an FDU2 higher than 25, and they satisfied the standards. They perfectly did, before the standards became available, what they were supposed to do. However, it is remarkable that there is no such system that was developed by using oxygen-air mixture. It's useless when the gas supply is wrong, when the supply gas is the wrong gas. And it becomes an issue when you use 3 gases instead of just 2. It also becomes an issue when you use higher concentrations of gases, such as xenon. The problem with low fresh gas flow and air in the circle system has been described by us many years ago, even in 2001. And actually, if you only have air as your fresh gas flow, and you have fresh gas flow lower than your minute ventilation, you will develop a hypoxic gas mixture within almost seconds. The lower the fresh gas flow, the faster the hypoxic gas mixture is created. So actually giving air to a patient in the wrong circumstances, low flow, can kill your patient. So there is a newer hypoxic guard system, and that is the electronically or software controlled version of the S-ORC, and that is currently used in the Draeger Zeus and the Primus. They use the same limits as I explained before for oxygen nitrous oxide, but also for oxygen air mixtures. And this S-ORC works in the conventional and in the target control mode. So now the question is, how good is this S-ORC? Because to the best of our knowledge, this has never been tested before. The criteria, the thresholds were chosen arbitrarily. So we don't really know how good they are. And the goal is really that these guards, the hypoxic guards, should prevent us from giving a hypoxic gas mixer to the patient. That should be very clear cut. So how effective are these guards? So I'm going to start with a case presentation. We have a female undergoing cystectomy, sevoflurane and oxygen nitrous oxide, sulfenta rocuronium, standard anesthetic. Target-controlled closed-circuit anesthesia was used with the Draeger Zeus. The target of SEVO was 1.6 to 1.2%. The target FiO2 was 30%, and the balanced gas was nitrous oxide. So it's a very standard anesthetic with a Zeus kind of system. So after 6 hours, the surgeon announces that the closure has started, and the anesthesia provider switched to the conventional mode. And this is what happened when we switched to the conventional mode, which is time point -4. We switched to the conventional mode and went from a fresh gas flow of oxygen of 168 to an arbitrarily high flow of 4.5 liters per minute, while the nitrous oxide fresh gas flow was below 100 mLs per minute. Because there is virtually no uptake of nitrous oxide anymore after 6 hours. It was increased to 13.5 liters per minute, totally arbitrary numbers, to very rapidly wash out the SIVO so that we could wake up the patient. However, at time point zero, the anesthesia provider remembered that the patient was going to be taken intubated to the intensive care unit. So there was no need to wake up the patient. The patient was old. It was expected to have a somewhat delayed recovery. They didn't follow your principles, Rick. And it was suddenly remembered, oh, we have to take this patient intubated to the ICU. So we can stop the washout of the sevoflurane, and we now can go to new fresh gas flow in a manual mode of 950 mLs per minute. Again, totally chosen arbitrarily. So this is clearly a fresh gas flow that results in an FDO2, the green squares, of 27%. When the fresh gas flow was high, we had 25%, which is determined by the ratios of these two fresh gas flows here. And here the S-ORC kicked in. The fresh gas flow was lower than 1 liter per minute, so the S-ORC kicked in and overruled the user, and the S-ORC made sure that the FDO2 was 27%. So the S-ORC was working perfectly here. However, when we look at the inspired concentration of oxygen, the green circles, we can see that the FiO2 quickly dropped below 21%. So the question is, how can this be? The S-ORC is working fine. It's doing its job, but we are developing an inspired hypoxic gas mixture. This was at 0.95 liters per minute, the sum of oxygen and nitrous oxide. So it's not really that low flow. When we reconstruct this case and we look at the mass balances, we can see that the amount of oxygen that was delivered for each time interval, 0, 1, 1 to 2, 2 to 3, 3 to 4 minutes, was 257 mLs per minute, which was the oxygen flow setting, fresh gas flow setting. If we determine that the amount of oxygen removed by the patient is about 200 mLs per minute, and you can argue about this number, maybe it should be closer to 150, but anyhow in this reconstruction of the mass balances we chose 200 mLs per minute, then we can calculate how much is lost through the pop-off valve if we assume that there is no loss of nitrous oxide, because nitrous oxide is still fully saturated in the tissues. So there is no uptake of nitrous oxide. Then we can see that the mass balance for oxygen is that we have 257 ml going into the system and 371 mL going out of the system. That has to result in a reduction in oxygen concentration in our system. It's a simple result of the mass balances. And if you do this calculation for several minutes in a row, you will see that the oxygen fraction in your system will go from 22.7% to 17.5%. So this is totally predictable if you look at the mass balances in this case. Based on that, we did a prospective study, and we really wanted to look at whether this was an anomaly or whether this could occur more frequently in clinical practice. So we did the prospective study, and we asked the question, can FiO2 below 21% develop with a well-functioning S-ORC? So we gave anesthetics to 8 patients who received oxygen nitrous oxide and 8 patients who used oxygen air. We used the lowest possible FDO2 over a wide fresh gas flow range. We used a ZEUS in the conventional mode, And we had several fresh gas flow FDO2 settings. And again, the lowest possible FDO2 that we used was according to this graph that is used by the S-ORC. So we used the lowest possible oxygen concentration in the delivered gas, and we saw what happened to FiO2. And the results are summarized here. I cannot go over all the details, but I can say that in some of the patients here, and in 100% of the patients with fresh gas flow of 1.25 and 1.5 liters per minute, we developed hypoxic-inspired gas mixture in the early nitrous oxide group. In all of the patients at 1 to 2 liters or 1.5 liter per minute fresh gas flow, and in some of the other patients around that fresh gas flow, an hypoxic inspired concentration was reached in the late nitrous oxide group. Finally, in the nitrogen group or the air group, we saw that the problem was even more severe. And what we noticed was that the problem was not so much at the lowest fresh gas flow, because there the S-ORC criteria were, for whatever reason, by chance, stringent enough, but they were not stringent enough between 0.7 and 3 liters per minute. In other words, these are the fresh gas flows where a lot of people are still very comfortable because they're afraid of using the really low fresh gas flow, but at the slightly higher fresh gas flow, they must be perfectly safe. Not true. The S-ORC does not prevent you from developing an hypoxic inspired gas mixture. So that means that the S-ORC criteria are not stringent enough at these, I would say, moderate low fresh gas flows. But the S-ORC did not fail at the lower fresh gas flows, less than 0.7, thanks to the stringent criteria of the S-ORC in that fresh gas flow area. So we are in trouble here, we are not in trouble here. In other words, the criteria were not sufficiently stringent in that area. How about other anesthesia machines? It's unclear what hypoxic guard systems that they use. It's unlikely that they use more stringent criteria than the S-ORC. In other words, we would have seen very similar results, or maybe worse, with other anesthesia machines. So it's not a problem related to the Traeger-Zeus machine. It's a generalized problem with all our anesthesia machines. So our case report, our theoretical calculations, and the patient study suggested that the current stringent criteria of S-ORC are still not adequate. So what should we do now? Should we use more stringent criteria? The problem is that these thresholds depend on the amount of oxygen that the patient is consuming, the actual oxygen uptake, and it really depends also on the machine configuration. And instead of trying to be proactive for all possible situations in terms of patient uptake of oxygen and for all anesthesia configurations, it's probably better to use target controlled FiO2 or FaO2. If we set a target of FiO2, then the machine is using a fresh gas flow and is using feedback from the measured FiO2 to maintain an FiO2 at that set level that we selected. So in that case, an S-ORC is not needed because we would not select an FiO2 that's less than 21%. But what about the manual mode? Well, in the manual mode, the S-ORC criteria are not stringent enough because that's when it would kick into place. And at the fresh gas flows between 0.7 and 3 liters per minute, an FiO2 below 21% can occur. So in my opinion, it's clear that we need another solution. And that other solution is to have an intelligent hypoxic guard system that is computer software controlled, where there is an adjustment of the FDO2 based on the measured FiO2 in all possible situations. We have actually analyzed the performance of one such system, which is the O2 guard by FlowEye. And the performance of that system is presented in a poster, and I cannot go into details on that. But what the machine does, it overrides the manual fresh gas flow settings to keep an FiO2 above 21%. So the conclusion is hypoxic guard systems, they're still somewhat a black box. We don't know a lot about them, but they have clearly evolved from mechanical, pneumatical system to software. Hypoxic guard thresholds, especially the S-ORC, are not adequate at this moment to prevent a hypoxic gas mixture. And I think that intelligent system should be based on FiO2 measurement to prevent hypoxic gas mixtures. Thank you.